Hello, Chem 1. We've been working our way through measurement. We've talked about base units. Today we are going to talk about derived units when we take base units and combine them. And we'll also talk a little bit about scientific notation. So let's get started. A derived unit is when we mathematically combine base units. We talked about how there are only 7 base units, but there is a lot more measurements than that. Things like volume and density. If we take a look here, volume is a length times a length times a length. So if we have a rectangular prism and we wanted to find the volume of that, if it was 5 by 1 by 2, we'd take 5 times 1 times 2, and that would give us 10 centimeters cubed. Notice that I've maintained my sig figs. We started with each measurement had 1 sig fig, we multiplied, and my answer has 1 sig fig. Density is another derived unit when we have mass and divide it by volume. It's a ratio of mass to volume. And so we can calculate the density of an object if we have its mass and its volume. So if we were going to do a sample problem here, this says what is the volume of a sample that has a mass of 20 grams and a density of 4 grams per liter. So I know that density equals mass over volume. So density, which is 4 grams per milliliter, equals 20 grams over volume. So the first thing I would do is multiply volume to the other side to get 4.0 V times 20. And then I could divide both sides by 4.0, and that would tell me my volume is equal to 5. All right, but if we look here, 4.0 has 2 sig figs and 20 has 3, so that means my answer should be 5.0 or 2 sig figs. Another way to do it would look like this. You could derive the volume before you put in the numbers. Here's another example. A piece of metal with a mass of 147 grams is placed in a 50 milliliter graduated cylinder. The water level rises from 20 to 41. What is the density of the metal? So there's something going on here called the water displacement method, which we'll do in lab. But the idea would be is if we put a volume of water in a graduated cylinder and then it rises, however much it rises, that's the volume of the object that we put in it. So in this case, if we took 41.0 minus 20.0, that would tell us that we have 21 milliliters. That's the volume of this piece of metal. And at that point, we could take our mass, 147, and we could divide by 21.0, and we would get 7. But once again, we have 3 sig figs in 147. We have 3 sig figs in 21.0. So this would be 7.00 grams per milliliter. The reason I know it's grams per milliliter is because we had 147 grams and 21 milliliters. If you want to look at that in another way, there's a different way to solve it there. Really, we only talk about volume and density in this class, but there are so many others, especially when you get into the realm of physics. You can see here the base units and how they're combined to form all these different derived units. There are so many. Even something like a newton of force, that's actually base units that have been mathematically combined to get to a newton. So sometimes we use a placeholder name like a Pascal or a Newton to kind of abbreviate the expression. Another measurement that we'll use in this class quite a bit is temperature. Temperature is the average kinetic energy of the particles in that material. In other words, how fast are they moving? Hot things move, the particles move faster than cold things. There are 3 different temperature scales that you'll come across. Celsius is typically how we record temperatures in lab. Freezing point of water is 0 degrees Celsius. The boiling point is 100. Celsius came from the word centigrade or 100, and it's based on the freezing and boiling point of water. Here are the countries that do not use Celsius as their standard measure. USA. Typically, Kelvin is the system of measure we use for mathematical calculations. The reason for this is because Kelvin does not have negative numbers. Absolute zero on the Kelvin scale is 0, and therefore everything is positive, which mathematically that's important sometimes. There are two lesser known or lesser familiar temperature scales. The one is very familiar to you because it's what we use here in the US. That's the Fahrenheit scale. There's also a Rankine scale, which is based on Fahrenheit, but it does not have negative values. So it basically scales everything up so everything is a positive number. Not used very often. So you will always have the temperature conversions. A lot of times what happens, since we measure in lab in Celsius, and we might want to convert that to Kelvin to use mathematically, or we might want to convert it to Fahrenheit so we have a better understanding of what that number is or where it is on the scale, you need to be able to convert from Fahrenheit to Celsius to Kelvin. Notice though, based on the equations you have, Celsius is kind of the middleman. It's really hard to go from Fahrenheit to Kelvin. So typically, if I gave you a Fahrenheit and said go to Kelvin, it would have to become a two-step process. If you look here, these are the equations you have on your equation sheet. You'll never be without them. You don't have to memorize these, but whatever you're solving for, if I'm looking for Fahrenheit, I'm going to use that equation. If I'm looking for Celsius, I could be, depending on where I'm coming from, I'd use these equations. And if I'm looking for Kelvin, this is the equation I would use. So let's do some examples here. The boiling point of liquid nitrogen is -196. What would be the Fahrenheit and the Kelvin? Notice it says significant figures here are not important because they're typically going to be used with a whole number. And whatever the whole number is, that's what you will keep. So if you look here, we've got Kelvin equals Celsius plus 273. So we would just put our Celsius right here, and we'd add 273, and we'd get 77K. Notice we started with 3 sig figs, we ended with 2. It does not matter. Whole number is what you're going to record. And then to go to Fahrenheit, Fahrenheit is 1.8 times the Celsius temperature plus 32. So we take 1.8, we'd times by -196, we'd add 32, and we'd get -320 Fahrenheit. So as long as you can read the equation and plug the numbers in correctly, you should be good to go. Here's body temp at 98.6 degrees Fahrenheit, and wants us to convert it to Celsius and Kelvin. So the first one we do is look for the Celsius equation that has Fahrenheit included. We're going to put in our 98.6, subtract 32, divide by 1.8, and we get 37 degrees Celsius. We could then take that 37, put it into our Kelvin equation, and that would give us 310 Kelvin. So once again, just familiarize yourself with those temperature equations enough so you can kind of do the math that goes along with them. Here's another one going from Kelvin back. I'm going to let you jot that down here, but bottom line, real basic math. Make sure you're plugging the number in the right spot, choosing the right equation, and you should be good to go. The last thing we wanted to cover today is scientific notation. I'm hoping that this is a review from math class or other science classes that you've done. The bottom line is we use the power of 10 to take really large numbers and make them more manageable, or really, really small numbers and make them more manageable. And in chemistry class, or in chemistry in general, you do things like count atoms and count molecules, and you'll get really, really big numbers, and writing them out would be really horrible unless you had scientific notation. So let's do some review. Bottom line, if the number is big, your exponent is going to be large or positive. If the number is very small, your exponent is going to be negative. And your M factor, or that initial number, has to be between 1 and 10. So if we look here at 700, we have to move this decimal somewhere, so we're in between 1 and 10. So we'd move it 1, 2, so we'd move it to 7.00, and we moved it 2 spots. 700 is a number that's greater than 1, and so therefore this would be a positive 2. Notice how I kept those 2 zeros. Why did I do that? It's because when I started, those 2 zeros were significant because there's a decimal there, and therefore I need to start and end with 3 sig figs when I'm going to scientific notation. B is different though. B, there's no decimal, so these zeros are not significant. So I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So I'm going to go, so I already know that this is times 10 to the 9th. because I moved it 9 decimal places to get to 5. And in this case, I will only need the 5 because it was the only number significant at the beginning. This is a small number. 1, 2, 3, 4. I can already put down this is times 10 to the negative 4. Why negative? Because this is a very, very small number, less than 1. And then I would just simply write 2.3. There were 2 sig figs here, the 2 and the 3, so there needs to be 2 in my scientific notation. If we speed this up here a little bit, this would be 8.0 times 10 to the, let's see, 1, 2, 3, 4, 5, 6, 7. 10 to the negative 7th. All right. We can go the other way too. We need to move this 5 digit places. So 2, 4, 0, and then 0, 0, 0. We moved it 1, 2, 3, 4, 5. This is a positive 5, which means this number should be big. If I would get like 0.00 something, I would know, okay, I went the wrong direction because the number got smaller. Notice I've only left the 2 and the 4 significant because that's what, oh, excuse me, I misspoke. See, I made a mistake. I was going too fast. This has 3 sig figs, which means this number needs 3 sig figs. The only way to make this 0 significant is to put a bar there. Because if I put a decimal at the end, then all those zeros become significant. I don't want that. I can make a better bar. There we go. Okay? This one would be 0.001730 because it's a negative number, so it's getting smaller. This is a positive number, so 2780. 1, 2, 3, 4. Boom, boom. And this 0 needs to be significant, so we put a bar there. I know I'm moving kind of quick, but really the new part here, hopefully, is just the idea that we need to maintain significance whenever we convert from scientific notation. Calculating with scientific notation, hopefully this is review, but at the same time, you're going to be doing this on your calculator. We're going to show you a trick that you may or may not know. Bottom line, when you're multiplying coefficients, you add the exponents, and if you're dividing, you subtract. So for this one, when we multiply these two numbers in scientific notation, we would multiply the 2 and the 3 and get 6, and then we would add these two exponents together, which means we'd have 6 times 10 to the negative 2. Notice how we've kept the correct number of significant figures. 2 is 1 sig fig, 3 is 1 sig fig, and our answer has 1 sig fig. This next one down here is division, so we're going to subtract the exponents after we do the math. 8 divided by 4 is 2. And then 10 to the 4th minus 10 to the 1 would be 10 to the 3rd. So 2 times 10 to the 3rd. On this last slide here, I just kind of want to show you something called the EE button. On your calculator, there's a button that has the EE there. It could be on a button, and it might be, you might have to second and then hit that button. But what that EE is it's putting a number into scientific notation so that you only have to put in the first number and then the exponent. So 3.4 EE2 is equal to 3.4 times 10 to the second. We'll work on this more in class. The value of this is it's telling your calculator that you're in scientific notation, and it will do things like the correct order of operations and keep things in scientific notation based on what you've typed in. It's a very important button in this class. We are going to get into really large numbers, and then when you type in, if you try to type this into your calculator, if you don't put parentheses around it, you're going to have problems because the order of operations will change, at least based on what your calculator thinks, and you'll get wrong answers. All right, so I would get used to using the EE button, practice using the EE button, so that you can be as effective as possible. So for instance, if I was going to do this problem down here, I would type in 2.40 times 6.022, and then I'd hit my EE button, and then I just hit the 23. And then the calculator is going to spit out the answer in scientific notation for me. Based on what we talked about today, hopefully you learned a little bit about derived units and some math that goes along with the more common ones in this class, and hopefully you got a refresher course on scientific notation and how to use those numbers mathematically. Good job today. We will see you next time. Have a good one.